So beyond that, being able to guess the answer to my 789 joke, you're also co-founder and CEO at Windscape AI, where you're using machine learning to help wind farms produce more energy. Tell us about that.
Yeah, so we are trying to make wind turbines more efficient. We're trying to make them generate more power and generate that power at lower cost. This will do two things. It will help wind energy be rolled out more quickly. It'll accelerate our transition to net zero, so to a world in which we power our planet without using carbon. It'll make our customers, people that own the wind turbines, more money. And because the turbines will be more efficient and generating more energy for lower cost, it'll also make the energy cheaper for you and me, for people that use the energy. We do this with machine learning. We do this by looking at data from turbines as well as weather, and I can get into that as deeply or as shallowly as you'd like.
Yeah, let's go. Let's dig into it. How does it work?
Okay, sure. So first, we take data from turbines. So all turbines have on board a number of sensors. In particular, you can imagine a sensor on the back of the turbine that measures the wind speed and the wind direction. One thing not everyone knows is that the way turbines operate these days, all turbines track the wind. Some people think turbines are installed facing north, and if the wind is from the north, that's great. And if it shifts to the west, you're just out of luck. I'm happy to report that for many years now, turbines have all tracked the wind. So as turbines are tracking the wind, basically, let's imagine the wind is coming from the north, the turbine's facing north, all is going well, and then the wind slowly starts to shift to the west or to the east or something. The sensor on the back of the turbine will pick that up, and it'll see that the wind is shifting west, and there's some control parameters that'll involve some delays or some dead zones maybe, but eventually the turbine will start turning to the west and follow that changing wind. Those sensors in the back are great in some ways. They provide obviously pretty good visibility into the wind at the correct height, so they're right up in the middle of the big circle inscribed by the blades. But they're also noisy in certain ways. The noise they receive is biased in certain ways. They're in the back of the nacelle, which is behind the blades. So every time the blades pass by, they generate vortices that come off the trailing edge and hit that sensor. And John is looking like this is one level too deep.
Wait, no, it's not.
They generate noise, but the noise is shifted. It's not zero centered.
So the wind turbine itself, as it adapts to where the wind is coming from, it makes the data worse that it's trying to use to detect wind direction?
Yeah, I would say it's actually not even a consequence of the turbine turning, although as it turns, the distribution of noise will probably shift. Even when it's not turning, though, there is still a lot of noise, and that noise is not zero centered. So we're trying to help turbines deal with this problem, also deal with problems of these sensors not being installed perfectly correctly, and or as they wear over the years, as they in some cases become miscalibrated over the years. We're trying to learn that calibration, learn that distribution, and kind of reset conditions to be straight so that the turbines are pointed the correct direction. There's some interesting studies showing that the median turbine right now, the median turbine around the world is mispointed by 6 degrees. There's other studies showing that the average turbine loses out on a couple percent of production because it's not facing the wind, it's not following the wind correctly. We're hoping to fix those problems using our neural network models. So that's kind of one part of the company. We also are taking this data from the farms and feeding it into modern weather models. So a fun fact about wind energy is both wind energy and solar energy are variable, right? So you have an electrical grid, you have a bunch of producers producing energy, feeding into the grid, it's flowing all around transmission networks, distribution networks, and then being sucked out by consumers using that energy. So if your light is on right now, those electrons were generated somewhere, probably within 50 or 100 kilometers of you, and it might have come from a wind turbine or a solar panel. Let's imagine you have solar panels and your light is on, and then a cloud just passes right over those solar panels, right? What happens? That production just drops, in some cases, nearly to zero. Or if you're a wind turbine, let's say it's windy, you're generating, and then the wind dies. Both of these factors, they're not factors that are controlled by humans. It's just something that happens to the grid, and the grid needs to be robust to that. It needs to react. So a second part of what our company is doing is trying to make wind itself more predictable. Um, the way we model weather the way we model weather in general is sort of changing right now. So since the 1950s, we've been modeling weather by running physical simulations on supercomputers. You can imagine a bunch of little voxels. Each voxel has, what's the air doing on the left side, the right side, the top, bottom, back, and front. What temperature is it? Maybe what relative humidity and some other factors. And then you just click play on that physical simulation, and you simulate all the voxels one time step at a time. This has worked fairly well for 7 decades. About a year ago, a few groups around the world showed that, in fact, you can train neural networks to do the same thing. If you just have a bunch of recorded historical data, you just throw it all in, train in, let's say, an autoregressive way, and it works. Cool, right?
It's nice.
Also, similar story to chatbots. Train autoregressive models on text, make them big enough, make the data set big enough, train for long enough, big enough computers, and you get kind of magic out. We're just seeing that now with models for weather.
Nice. Yeah, and autoregressive there meaning predicting the next token in a series of tokens in the case of like a large language model. So when you're speaking to a generative AI model that is outputting natural language or code, it's outputting the next tokens. It doesn't have future information, future tokens that it's outputting. And so what you're describing is similar in the sense that you have all of the data on, say, wind up to a point in time, and you're trying to extrapolate forward. Yeah, autoregression.
Yeah. Some people would call this an unsupervised approach or a self-supervised approach. Just requires a big data set of what's happened in the past, or in the case of chatbots, what was written on the internet in the past. And you can train those models then.
Nice. Yeah. No explicit labels. Very cool. And that's great because then it means you have a lot of data to work with typically.
Exactly. And it's turned out it's one of the lessons of the last few years is right. Training models on these really huge data sets is what enables them to perform really well.
Nice. Certainly exciting things that you're doing there on both fronts. So both with helping turbines track wind direction more effectively, and so getting more bang for each buck out of each turbine, and then secondarily using ML to make wind direction more predictable writ large across regions. And so I guess that allows, and you might have already said this, but, uh, and I'm just kind of being foggy, but how does that information get used by, say, an energy provider? How can they, if they know wind direction, and you also gave the example of solar, like, does this relate to the way that different renewable energy sources interplay within a grid?
Yeah, very much so. Again, we could jump in here for like 35 minutes, or we could talk, for 1 minute. The problem with these renewables that I mentioned is that they're intermittent, so that they're kind of coming online and going offline, not in a way that's under human control, just driven by nature. The grid needs to be able to react to this. We can do this in a couple ways. So one simple approach we could imagine is we take a bunch of batteries, we put them on the grid. What do the batteries do? Well, let's say they charge up when it's sunny and windy, and their charge goes up to eventually 100%, and they hang out there at 100% for a while. And then as soon as the sun dies, as soon as a cloud comes over or the wind dies, they start discharging into the grid. So this is one approach we could take. In order to use those batteries most optimally, you really want to know, when is it going to be windy? When is it going to be sunny? You don't want to just be reactive. You want to anticipate periods of sun or wind so that you'll be ready to charge. The way the grid actually works is there's a real-time pricing signal that tracks kind of like how much energy is available and at what cost. If it's very sunny, if it's very windy, the energy is very, very cheap, sometimes literally free. So what you want to do if you own batteries is you want to charge then. Later, when the wind dies, the price goes up, and you want to discharge then, and then you're paid that difference in price. This is already the way the grid works, but to make it more efficient, to make it more cheap for people, and to make it more resilient, we need to make all these natural factors more predictable. And that's where the kind of weather modeling comes in.
I imagine that in a lot of grids around the world today, we might not have the battery or renewable capacity always available. I suspect that that's the case actually on the majority of grids. Obviously, we hope to fix that as soon as possible. But today, there's probably also an advantage with this kind of planning that you're describing to allow us to know, hey, we're going to have to turn a traditional kind of coal or oil fired plant on in anticipation of a prolonged stretch of both darkness and no wind, say.
Yeah, absolutely. Absolutely. So you mentioned a problem of if there are long stretches of no sun or wind, then we need to turn on dirtier fuel sources like gas and coal, and that's absolutely true. What's less immediately obvious is that by making things more predictable, just by knowing that period is coming, we can do certain things to prepare for it. But if you get into how energy is actually moves around on the grid and is bought and sold and traded, uh, having greater predictability does enable you to do some of those things. And this is really important to work on right now. Certain grids, if you start out at 0% solar and wind and you slowly add a little bit of solar and wind, 1 or 2%, the whole grid kind of sort of still works. But as you push that percentage higher and higher, and a higher fraction ends up being intermittent, it can start to cause problems. So much so that without all these batteries, which are not yet deployed everywhere, like you said, you hit a limit and you need to keep using coal and gas and these dirty sources because the grid can't take any more wind and solar. So we're all around the world in the process of switching one step at a time, 1% at a time to wind and solar. We are trying to kind of accelerate that process however we can.
And it's interesting. This is digressing from possibly your expertise, and it's certainly from the line of questioning that I had planned. But when you described the mix of energy sources that you were interested in using, you didn't mention fusion,
Hmm.
which I suspect was deliberately left out.
Sorry, I meant to mention nuclear fission, and that is an important source in the U.S. and in many countries. Um, I didn't mention fusion. It doesn't work yet. If it does work
Yeah,
someday, that would be
yeah,
amazing. That'd be
that's
great.
true.
Um,
Yeah, yeah, yeah,
if we never get to fusion, we will need to power the world on those other four: wind, solar,
yeah, yeah, yeah,
hydro, which we are using quite a lot in the US now,
yeah.
and fission. If fusion does someday work, that will be amazing. We will build those plants as quickly as we can. It might be many years, many decades before they're all rolled out. So in the
Right.
meantime, we still need quite a lot of wind and solar.
Yeah, yeah, yeah. That makes a lot of sense. And as soon as I asked the question and you started answering, I started to feel silly.
No,
Thank
no,
you.
no. Yeah. Even fission, though, even fission, for whatever historical reasons, and this is the edge of my knowledge now, it's really hard
Mhm,
to build these plants. They're very slow and very expensive. They're more expensive per megawatt hour than wind and solar.
mhm,
So
mhm.
they could be part of the right answer for the next decades, but the they're not a silver bullet.
Yeah, they do fill that gap when it is dark and there's not enough wind.
For
They
sure, for
fusion
sure.
they yeah, yeah, yeah. The
Yeah.
fission reactor
Base
can
load,
kick in.
exactly.